someone trying to answer so we can keep on going, okay? First of all, I would like to thank Professor Ali to invite me to give a lecture on functional analysis. That's my favorite subject. I am a harmonic analyst and I have written a lot of paper in harmonic analysis, functional analysis, complex analysis, statistics, and so forth and so on. So please feel free to contact me, call me, okay? I send to you this. I don't know if Professor Ali gave it to everybody. Did you, Ali?
Yes, I forwarded your
Okay, and this is a part of a book that I am writing with Professor Ed Quazai. Okay, so you probably can see that. You have that over there. So I have to take it off things, put it off things. So I did this note just for you. Okay, so please ask any question whatsoever. You stop me anytime. We are very relaxing. I always use my cup. That's Auburn University. Okay, and let's get started. So what I'd like to do here is giving a overall picture of functional analysis. Okay, and functional analysis at this level can be described as vector space, normed space, metric space. We're going to see some difference from metric and vector space, normed space. Then linear transformation, linear functional. This is the basically for you to go on. So the next step is four major theorems that you have in functional analysis. Is the closed graph theorem, the open map theorem, and the uniform bounded principle and Banach theorem. That's are the four major theorems at this level, okay? So what we're going to do here is just get the basic. I am going to start with vector space, normed space. I am not going in much detail. I want to give a picture what's going on, okay? Please ask any question and stop me anytime whatsoever. Now, one question is this. Is everybody can see my board in here?
Yes, Prof.
Yes.
Let me put it the other side in here. Okay. Now we have vector space. Then we're going to normed space. Then you go to metric space. Okay. Then you go for linear transformation. Okay. Linear functional. That is the basic stuff that going. Is everybody can see the board?
Yes. Yes, Prof.
Excellent, super. You know, the good thing about this pandemic is that we activate the technology. So now you guys are in Pakistan, I am in Colorado Spring, and we talk like you are in the next room. That's excellent. Okay, now, what's a vector space? Pick a set X you define a operation you call plus, and you define a second operation that you call scalar multiplication. And this is a set, but you have these two operations. This operation plus is closed. That means if I pick a x in here and y, and x plus y in there. So if I pick element in x, and if I add this element, then is in x. That's what we call the addition. Okay, then you have the scalar multiplication. You have the real number in here. So that if you pick a real number and pick a x in x, when you multiply, this is in x. This is essential to operation that must be there. Okay? Now, this over here not necessarily means we call addition, but it can be the way that we define. You can define a addition like, suppose that I define a addition like this, x and y, like this. Okay? So this addition over there can be anything whatsoever, but the important in here is if you pick an element in x, when you add this element is in x. Okay, have to be, so that it means it's closed on the addition. Okay, and this over here, if you pick a x in x and you multiply by any number, and they still in x. Okay? Now, what do you do with that? Okay? Now you have the property. I am going to write down the property, even though that you have on your notes over there, because I have a question to ask soon I finish write this. One is this. If you have x plus y is the same y plus x. That means it's commutative. Any way that you do it to add, that's okay. It's commutative. 2 is x plus y plus z. I maybe add this here. Then I can add like this. If this happens, you say that is associative, okay? This basically means you can add any way you want, okay? You pick 3 numbers or you pick 3 vectors, then you can add any way you want. So the other thing is this. There is, which is unique, a vector 0 in x, such that when you add this, you get x. And this we call neutral element. Okay? This is 0 doesn't mean necessarily that is the 0 that you know from the real number. Okay? That you call neutral element. Okay? The other thing is this. Given a x in x, there is a x prime in x, so that x plus x prime is equal to x prime plus x is equal to 0. Now, this is the additive symmetrical. If you are on the real number, if you pick x is equal to 2, x prime will be minus. And this property over here are very, very important, because this over here tell you that x with the operation plus is a abelian group. Is a group. Okay? We are not going to touch this, just for your information. So the next property that you have is this. You have alpha x plus y. Alpha is an element in R. This is alpha x plus alpha y, where alpha is a real number and x and y is in x. So that means you can distribute. That's a distributive. And the sixth one is this. If you have alpha plus beta times x, you can distribute that for all alpha and beta on the real number and the x is in x. That's called the distributive. Okay? Now, let me take a little peek over here on okay, the other property is this. If you have alpha and beta x, now I am using the second property, right? That's the same as alpha beta times x, where alpha and beta are the real number and x is in x. Okay? Now, 7, 8, that's the last one. Okay? There is a number 1 in x, so that, well, this over here is for all x in x, 1 times x is x. Okay. There is another property over there that in general. Now, if you have a set, this can be any set whatsoever, okay? Now you have an operation over here and have two operations. These two operations are closed on the addition and the scalar multiplication. If it satisfies all this property over here, okay, that means x plus point is a vector space. Okay? Now I have the following question. Where did this come from? Does anybody have an idea? Where did this come from? Where did this definition come from? Someone having somehow in some way come up with this property over here? Is anybody hear what I'm saying? Hello?
Yes, Prof, we can hear.
You can hear, okay?
Yes,
Where
Prof.
did this come from? The whole idea in analysis mathematics, the basic structure is the real number. Everything that you do is a generalization of real number. Okay? So this over here, if you take x, the real number, take plus our usual addition and our multiplication, r plus 1, okay, that was a gift, okay, because you know 2 plus 3 is 3 plus 2, 2 plus 3 plus 4 is the same as 2 plus 3 plus 4. Did you get it? So
Yes, Prof.
everything over here is mirror on the real numbers. Now, the only property that you don't have over here is the existence. If on the real number, if you are on the real number, given a x on the real number, there is a x prime on the real number such that x times x prime is 1. That is the symmetrical with the multiplication. If in addition to this satisfies this condition, then this vector space would be called a field. But the whole problem is this. All this property over here come from the real number. We are just caught with the real number. Is everybody understand what the point I want to make it?
Yes.
Please, Nazar is going to be my spokesperson, right? Because the other people don't want to talk. There is a person over here called Nagni Fatima. That's a Portuguese name. Is that common in Pakistan? Fatima? That's a Portuguese name. I am from Brazil, original. Okay,
Yes,
guys.
Prof.
Now I
It
want
is
you to try to
particular name.
understand. Okay, go ahead.
Are you asking about the name of Fatma?
Yes.
Yes, Prof. It is very particular and common name in our country.
Oh, that's it. That's it. That in Portuguese in Brazil, in Portuguese, this name is very common. But there is
Wow,
a
that's
accent
great.
in it, Fatima. Okay.
Yes.
But anyway, I want you guys answer the question. Saying is the concept of vector space. Remember, what I am doing over here is going to be an overall picture. You're going to see things that you probably didn't see because you look like the definition over here. The question, where does definition come from? Is that sky when there was snowing and for this definition? Or it was on the mango tree over there? No, that's the real number. There is a saying that we quite often say, God gave us the natural numbers and the real number. The rest is imagination of the man. Okay? So the real number is the basis for this. The thing that I am going to do in here and show you is the real numbers everything. Is everything. So you generalize. So this over here, vector space, is a generalization of the real number. Now remember, there is a property on the real number that you don't have on the definition of vector space. Is the inverse, the multiplicative inverse, because this over here is the additive inverse. And this will have if the vector space is a field. Okay? So 1 to 8 is the definition of vector space. And this additional condition over here, the vector space becomes a field. You have the vector space. Is everybody understand what I'm talking about, what I want to get? Go
Yes,
ahead,
sir.
people. Good. I like to see yes over there. Everybody speak English, right? I don't speak.
Yes, sir.
Oh, very good. Safa. Is that Safa? I probably pronounce your name. I am pronounce like Portuguese, even though that I speak few languages, but I don't speak either Arabic or okay.
Yes, Professor.
So what I want to stress is all this definition that you're going to see, vector space, normed space, come from the real number. We just naturally generalize. Remember, I used to say quite often, mathematics is not matter of opinion, is not matter of culture, is not matter of politics, is not matter of religion, okay? Have to be the way that there is a sequence how the thing is. So the vector space is a mirror of the real number. Can I keep on going?
Yes, Prof.
Yes.
Very good, Nazara.
Yes, sir.
If anybody have any question, please ask. I am not on the hurry. I take life as easy as possible. Since you have one life to live, let me enjoy every single minute. Okay? Now I am going to the next step. Okay? So the next step is going to be, now see what you have. You have a X in here, you have an operation in here, in the two operations, right? Now let me give an example. In the book, the notes I have, you have plenty of examples. Let me give one over here, okay? I am going to take X is equal to N. N is an integer, okay? So, what this set over here? This set is x1, x2, xn, where the xi's is a real number. Now, that's the set of Rn. So, I would like to make this a vector space. So, what I have to do is I pick one guy in there, x1, xn. I pick another guy in there, yn, right? So I need to declare what the meaning of this. Remember, in mathematics, all the theory that you have, Banach theorem, closed graph theorem, all this is come from a very natural way. Okay? So, if you look at this over here and I want to define, if there is justice on this word, you make this definition over here, x1 plus y1, x2 plus y2, xn plus yn. And that's a natural way to define. Okay, you are each coordinated. Now you see this is an element in Rn. Why? Because this is a real number, this is a real number, a sum of a real number is a real number, so each of these guys over here are the real number like the definition. So that means it's close on the operation over there. Okay? Then you want to define what you mean by this. What's the natural? If there is injustice on the word, this should be alpha x1, alpha x2, alpha xn. Now I need this guy to be in n. This is a number. This is a number. Alpha is a number. Right? And X is a element in R. X1 is in R. So when I multiply alpha times X1 is in R. So
Yes.
each of this is in R, so this whole thing over here is in Rn. Is that about understanding? I am going slowly to try to explain details of the things, how this works. Plus, everything comes from the real number. See over here. So in order to X, to be in R, and each of these guys must be in R. But if alpha is in R and x1 is in R, alpha times x1 is in R. See, because R is a vector space. So this whole thing is a vector space. So Rn is a vector space. Is one of the most important one. Does anybody have any question? Remember, I am going details in all the things that I'll be talking over here, okay? So this is a vector space. Let me give another example over here. We have several examples, but I'm going to choose one. In the book, you have several examples, have matrix. However, I am going to one space that you probably going to see many times on your life is this. There's example 1, let's see example 2. Let me put in the red. Okay, I am going to take x as the continuous function on 0, 1. What this over here is the set of the other function from 0, 1 into R such that f is continuous. Okay? Now, I want to make this a vector space. Question. What do I need in order to have this a vector space? Anybody can answer to me?
Sir, first we have to show that it is closed in addition.
Well,
And
So we
second,
need
we have to show
addition
that
and
the scalar multiplication
multiplication.
should be in the closed.
Multiplication.
yeah, but you know, you miss one observation before. You said they had to be closed, but closed in what sense?
So we need
Remember,
two operations.
say again.
We need two operations, addition and multiplication.
There
Define
we
numbers.
go. There we go. We need two operations. Then after you have the operation, we need to show what, I don't know, whoever spoke, that is closed on the operation. Did you get it? I am going details. And some of the things you probably have seen over here, okay? But we're going to get a little bit more complicated as we go on. Does anybody have any question? So I need to define the operation. So I pick a function f. And g in there. So I would like to define what I mean by f plus g, right? What I mean by f plus g, that's a function. Basically, depend what I am going to define in here, okay? That means the sum of continuous function is a continuous function. That's basically boiled down. But I need to define this. This is a function. So the way that you're going to define this over here is this. You pick f plus g at a point t, which is in 0, 1, okay? And define this f of t plus g of t, okay? Now, that's for all t in 0, 1. Okay, let's try to understand. It's come back now to the real number, okay? I am trying to define this. I said my definition is this. When I evaluate at a point t, that's the way I'm going to define. Does this make sense? Where this guy is? Anybody can tell me?
R, real numbers.
Thank you. Who is talking? Is that Fatma?
Sir, Anam Riaz.
Okay, I mean, okay, excellent. And this is a real number. See, the functions are functions from here in the real number. So this is a real number, and this operation over here, believe it or not, this operation over here is the operation on the real number. And this operation over here is not the same as this operation, because this operation over here is among functions. Can you understand what I'm talking about?
Yes.
Can
Yes,
you
Professor.
can you agree with me?
Yes, sir.
You see,
Yes, Professor.
this is a real number, this is a real number, so the sum of real number is a real number, but this is the addition of the real number. This is not addition of this. We are used by abuse of language in here, but this plus is not this plus, and that's the way I define. Okay? Now, the other one, you pick a alpha on the real number and pick a f in continuous function of 0, 1. So you want to define what means by this. That's what you would mean. Okay? And this at t would be alpha f of t. Now let's try to understand what I wrote in here. Okay? That's the scalar multiplication. What this scalar multiplication is? This scalar multiplication is on the continuous function. What this over here is? Can anybody tell me?
Hello, Professor.
Multiplication of two real numbers.
The real number. Excellent. I love that. That's a multiplication of the real number. So that's a real number. So this whole thing is a real number. But this scalar multiplication, let me put some color in here. Black. It's not
Hello,
the same as
Professor.
this. Okay? So, the continuous function,
Hello, Professor.
yeah,
Is
Go
it
ahead.
necessary? Is it necessary to choose alpha from the set of real numbers?
not necessary. You can choose for any field. So when I say this, I said the vector space that I define on the real number, but you can use any field, like the complex number, the quaternion field, any kind of field. Okay? Now,
Okay, sir.
we are use the real number in here. I could use complex number, any field whatsoever. Did you get it? But what I am stressed is at the operation, because you need two operations. You need two operations. You need two operations in order to define a vector space. Now, you can check yourself. This two operation plus on the continuous function, scalar multiplication satisfy all those 8 properties. You can check this over here. So you should do this at least once in your lifetime. Check detail by detail. Because there is a big difference between the complex field, okay, the complex number, and R2. We're going to talk about it. Is anybody understood what I'm talking about?
Prof, I
Is
have a
it-
question.
Is anybody understand what I'm talking about? Is
Yes,
anybody have
Prof.
any question? Look, I want you to feel very comfortable and ask any question whatsoever that you feel necessary.
Prof, I have
And
a question.
okay, go ahead.
Prof, you talk about a field of quaternions. Am I right? You
Say
talk
again?
about you talk about field of quaternions, as you have asked that we can take any field from
That's right.
complex
Yeah,
number.
that's
Then
right.
can you please give a little bit detail about group quaternion, field of quaternion? So as
Yeah,
is it that which we study in group theory, group of quaternions, Q8? Is it like that?
yeah. I probably delay your question for a little bit more
Okay,
ahead
Prof.
because
Thank you.
remember a field have the all property of vector space
Yes.
plus one is the inverse, multiplicative inverse. You have several fields, okay, in this complex number. So since I need more time to do, so then it's derail what I'm doing.
Okay,
But I
Prof.
will answer to you about this, okay? Is anybody have any question?
Yes, sir. Sir,
Go ahead.
you have talked about that we can choose scalar multiplication from any field. So
Any
if we
field.
in example one, like this, there's the alpha. If we
Yeah,
took alpha from complex number
complex number.
after
Yeah.
uh, after multiplication with x, so will it not be a complex number?
Yeah,
So
exactly the
it will
same.
not belong. It will not belong in Rn.
No, it does belong. You have to
Uh,
define the complex multiplication the way it is. But it belongs. It doesn't matter of field over here, you use over here. You know, this have to be, you can use any field, so you can say the vector is space on the real number, the vector space on the complex number is a little bit more complicated, the property, because the real and imaginary. Okay? See, if I use complex number over here, okay, and this is the x, so the complex number is closed on the multiplication. So when I multiply this over here, this is going to be on the complex number. See? See, this is a real number. Every time a complex number is a complex number. A real number is a complex number. A real number is only complex number. Okay?
So if you multiply a real number with a complex number, it will
You
be a
get,
complex number.
yeah, but you are taking this over here as a complex. You are not using this over here. You are using this, right? See it?
Okay, sir. Okay, sir.
Did you get? This should be A1 plus AB1, AN plus ABN. See over here where AN and BN are a real number. Not this anymore.
Okay, sir.
So when you define, you have to be careful for the addition and multiplication be closer up. So it's a matter of you look the conditions, the fields and so forth and so on. Okay, what the fellow, I don't know what his name, who was talking about was Assad. I don't know who
Yes,
was
sir.
talking. You know, you just do this over here because he was saying that since this are real, if you multiply by a complex number, this is not be real, it should be a complex number. What I'm saying is this. So you have to properly define when you use the field. Okay?
Okay, sir. Yes, sir.
Okay.
I got it.
Did you get it?
Yes, sir. I got it.
One thing that I want you to, I want to give a overall picture and go in details about how the things works out. Okay. As I said, mathematics, not politics or matter of opinion. Okay. You have to define properly. Okay. Now we're going to put another structure on the vector space. Remember, my vector space X, that's a vector space on the real number. We are just to the real number, right? So I am going to define norm. And this is very important to understand the concept, okay? So a norm is a function, which I'm going to use like this, from X into the R plus, which send X. So this over here is a positive number, right? Or zero. See it? Now satisfy the following condition. Norm X in X is equal to 0 if and only if X is equal to 0. 2. X plus Y X is less than X plus YX. Third, alpha X is absolute value X for all alpha on the real number, okay? If it satisfies all this property, we say that XX is a norm in X. That's the definition. One of my PhD students generalized this notion over here. I am not going to mention this condition over here, for example. Okay, and I gave a talk on our project that we have in Africa and Senegal about this condition over here is important, but it's not that too much important. You can. I'll mention this. Okay, now that's the definition of norm. What a norm is, what the idea of norm, what you measure in norm. You measure some distances, right? That's what you're doing. Okay, for those that are more advanced in the like topology, when you introduce a norm, you are introducing a topology. Okay, you are introducing topology, so this is very profound in here. Okay, now question is, where did this come from? Where did this come from? Do you think that's coming from a mango tree? We have a lot of them in Brazil. I didn't find any of them. Okay, that's come from the real numbers. Okay, the real number. If I take X, the real number, I take the norm in X as absolute value of X. It satisfies this property, satisfies this property, satisfies this property. Right? On the real number, X is equal to 0, that's absolute value, if X is equal to 0. 2, X plus Y is less than X plus Y. 3, alpha X is absolute alpha X. See it? That is absolute value. Now, what do you do it? You pick a space, which is a vector space, have an operation, because if you didn't have the operation, you could not do this over here. If you were not a vector space, you could not have this over here. Okay? So, we just copy what the real number is, right?
Okay,
You get
bro.
it? Okay, so everything comes from the real number. Now, the natural question, what do you do with that? Okay, let's give some example and let's see it. Remember, now we have the following situation. You have a vector space. Now you have a structure, you have a norm. A norm is a way to measure the distance, right? Like this over here is. If you have a real number, if you have 0 over here, you have 2 in there. What is distance over here?
2.
2, right? You see, you are talking about distance. If you have this 3 and 4, what is distance over here? So 1 is what? 4 minus 3, right? So what I want to stress is the thing that we are in more advanced come from the real number. Everything that you're going to see in analysis, the basic structure is the real number. Does anybody have any comment? Does anybody have any question? Please feel free to ask any question. Okay?
Okay, Prof.
So now we're going to look some example of norm. Okay, we're going to see some example of norm. Then what you do with this? So the natural question, what do you do with this whole thing's in here? So remember, I start off with a house. There's a house. I start put stuff inside the house. I put a bed, so if you don't have bed, you cannot sleep. Okay? Well, what do you need? You need a refrigerator, and you have in here. Okay? What else do I need?
Okay, Prof.
We need a computer over here, right? So I am filling the house. See, I start with a space, a set. This is a set. I introduce 2 operations. I introduce another operation. So I am filling up the house. Is everybody understand what I mean? What the point I want to make?
Yes, sir.
So the question is, what do you do with that? That's what we're going to do now. Okay? So I am going to give some example. Okay? Remember, when someone says let X plus be a vector space, this is a set, these 2 operations satisfy all these things. If in addition satisfy this condition, it's called field, because you're going to see a lot when you look some theorems and you say let X, Y be a normed space, because now we are in the following situation. X plus is a normed space. Let's see some example. The example comes the real number, right? When make X is equal to R, make the norm X being absolute value. And this is a norm. That means satisfy all this condition. By the way, do you remember how you prove this over here? Does anybody have any idea how you prove this very quickly? Someone of it. That's a real number. That's the baby stuff. Can anybody tell how I prove this?
Sir, by
Hey,
using squares, by using power 2.
Okay. Let me see if I understood what you said. You said if you square this over here, so how I get rid of how can you spin this over here?
The mode of square is equal to x plus y whole square.
Excellent. So this is x squared plus y squared plus 2. What she said, this over here is the same as x squared. This over here is this. Then what? So where to go? What the next step?
This will be less than and equal to mode of x plus mode of y, because we have an additional term 2xy here.
Who is talking? Aman? Ria?
Anam.
How you
Anam.
how you pronounce your last name?
Anam Riaz.
Ananya. It's excellent. What she said was this over here, x and y is less than this over here. See? Because this could be negative, this is always positive. So this over here is less than this plus 2 absolute value x, and this is absolute x plus absolute y is square. You cancel out, you have this. Excellent. Okay? Some are not so easy, okay? But this is easy. But anyway, is anybody have any question? Please, I want you to talk and ask some question. Okay? I'm sure that everybody speaks English, right? I speak Portuguese or Spanish, we can do too. Okay. Now, second, let's make x, let me put this over here, R2. Okay? So, what I'm going to define is, I'm going to define what I mean by this in here, right? R2, which is x squared plus y squared is square root, right? And this is a norm. The other norm that you can put in here is this. You can this plus this. This is a norm. Satisfy all those conditions. Other norm that you could put in here. Usually they call this over here. Let me use the notation over here because that's what you have is two norm. And this they call one norm. This called infinity norm. That's the maximum of this. All this are norm. More yet, if you have x and y, and you have p over there, then you have x to the p plus y to the p raise 1 over p for p bigger than 1. That's also a norm. Now it's a little bit more complicated to show some of this inequality in here, right? Okay? So this on the space. And remember, even though that this are norm, later on, if I have time, I show that all these norms are equivalent. Okay? For example, you have some pair of inequality on this stuff. Look at this over here. This in here is the same as the square root of this, right? You get it?
Yes,
But this over here is less than this square plus that sum, right? So this over here is the same, and this is less than, see it? If I add this guy, I have x plus y is less than twice is square root. See? See, that's nice inequality. So the other thing is this, look this, x is less than this. Okay? Y is less than this. So the maximum of this is less than this too, right? You see another inequality? But anyway, this is a norm, and this is the norm. This norm over here is the most popular one. That's the one people use this. Okay. Now, you can do some geometry over here to life becomes a little bit more exciting. Well, let me stop over here and ask, is anybody have any questions about these norms in here? All these are norms. That means satisfies those three properties. Okay? I am not going to prove unless you want me to, okay? Because I want just advanced and show. So in Rn, these are the norms, okay? And these norms usually are equivalent, whatever that is, you're going to see later on, okay? This is a norm. Now, there is some geometry in here, okay? Suppose, for example, does anybody have any question? All those norms satisfy this condition. So what did you get there from here? The definition of norm comes from the real number, stuff that we know very well. We know how to prove this, we did prove this, right? Now, depending on the norm, the situation is complicated, okay? So, but the idea is the original idea of norm on the space coming from where? The real number. Okay? Now, let's see some geometry in here. Okay? Suppose, usually you call, I'm going to S2. That is the set of x and y in R2. So that the norm x and y R2 is equal to 1. That's called the unit ball. If you put this less or equal, that's the soul, the inside, right? If I put this over here, this is just the outside. Now, the reason I mention this over here is because, if you start topology, okay, we have this is a neighborhood of 0, whatever that is. Okay, now look what this over here is. Now, you ask me, Dr. D'Souza, you have all these norms over there. What one should I use it? Hey, everybody's so quiet over there. I know that should be over here.
XY norm 2.
Huh?
XY norm 2.
Look, you can take whatever you do it, you can take any of those norms. Some of the norm data you pick over here would be easier to deal with. This norm over here is the most used one. But you can take in this norm. Whatever you want to prove with this norm, you can prove this norm, you can prove this norm, you can prove this norm over here. Okay? Of this, you're going to see is slightly different in here. However, in terms of results, you can use any of them. Most of the people who deal with functional analysis, complex analysis, matrices, all this, they use this over here. I myself, I love this over here. I use that over there. But let's see. Does anybody have any question? No question?
No, Prof.
So let's see what this over here is. Okay. So I am going to do this in the following sense. I am going to pick this S2, the set X and Y, such that X and Y 2 is equal to 1. Let me put some green on your life. S squared, the X and Y squared, such that X and Y 1 is equal to 2. Okay? How about red? The next one. S squared is the set of X and Y in R2, X and Y infinity is equal to 1. Okay, I'm run out of color. S squared is the set of X and Y in R2 such that X and Y P is equal, you don't see much of this over here. Okay, let's see geometrically what this is. Now, recently, me and my collaborator, we have published a paper about norms, which I do this over here, which is very nice. It was published in a magazine in Brazil. It was published in Portuguese, but I kept the English version. So I am going to send it to Professor Ali, also Miss Nozara, so they can send to you guys. It's very interesting, okay? It's not bad. Now, let's see the geometry of this over here, okay? Now, let's go to the blue. What the blue says? The blue says is square root of x squared plus y squared is equal to 1. So this is y squared plus y squared is equal to 1. So geometrically, this is a circle. Center at 0, 0, and the radius 1. So basically you have this over here. So this is 1, this minus 1, this is 1, that's what. See it? That's what this is. Okay, so it's a circle. So if I put less or equal in here, then include this over here, the whole thing inside. Okay?
Okay.
Anybody have any question? Now let's go to the green one. So what the green one? The green one was x and y. One was x plus y is equal to 1. So I have to graph this, right? So if I put x and y positive, that's x plus y is equal to 1. So this goes to 1 and 1. So I have this piece over here. Okay? If I put this negative and this positive, I have this over here.
Prof,
Go ahead.
Prof, please use black or blue marker. I think it means we cannot see it clearly.
Or you cannot see it. Okay.
Yeah, Prof.
Oh, let
Thank
me-
you.
No problem. I want people to talk. Because it looks like that I'm talking to the computer by myself, right?
No, Prof, you are talking with us. It's very nice to have a lecture from you.
Thank you. Okay, let's graph this. So if I throw away the x, the absolute value, if this is positive, this is positive, this is 1, this is 1, so I have this little piece over here. Now if this is negative and this is positive, then it goes in here. If this is positive, this is negative, goes in there. See it? Remember, the other one was a circle, right? But this is not a circle anymore, right? Now, let's see the next one was the maximum. Is equal to 1. Let's see. If the maximum is x, this is equal to 1. Or this in here, right? So what's the graph of this? This 1 and a minus 1. What this? 1 and a minus 1. This square over here, right? See it? We have this, and the other one that we have was this, right? Okay? Now let's do one that nobody wants to like to do it. Is xp plus yp p in here is equal to 1. That means xp plus yp is equal to 1. No matter what, okay, you're going to hit in here 1, you're going to hit minus 1, you're going to hit negative 1, and you hit 1. Now let me tell how this is, okay? This going like this. See it? That's the way.
Yes.
Now let me tell you what's interesting. If p is equal to 2, this becomes a circle. Okay? If p is equal to 1, this becomes this over here. P infinity. P infinity. This becomes this over here. Okay? Now, if p is less, that's for p bigger than 1. If p is less than 1, you get this over here. Wait, let me put some coloring here. This is for p less than 1. Now, if p is less than 1, this over here becomes this. You see it? See it?
Yes.
If p tends to 2, this becomes a circle. So the situation is this. I am going to assemble all of them together. If you be interested in see this stuff, I have nice pictures over there on the paper. Ms. Nozara had a copy. Ali, I believe, have. the newlywed lady, Misha Motion, also have this, but I am going to send to Misha, or I mean to Ali and Nazar, so you can get from this. And you have my email on this over here. So if you need a copy, if you don't get, just send to me your email. I will send to you. Does anybody have any question about this over here? There is a problem that's interesting. The problem is this. Limit of x and y, p, as p goes to infinity, this is x and y infinity. Now you can see why. See p over here. As you get bigger, become a square, see? And this is the maximum, the slope, right? So geometrically you can do this, right? This is an interesting problem in here, but you can see geometrically. Okay, does anybody have any questions? This is a nice class. Nobody have any questions? Does anybody have any comments? Now, according with Professor Ali, they always give, you know, 5 minutes, 10 minutes, 20 minutes, okay? When do you guys need to be, Professor Ali, when do you guys need to have a 5-minute break or 10-minute break or 20-minute break? To me, I keep on going, okay?
Yeah, bro.
Does anybody have any questions? Does anybody want to stop for 5 minutes or what?
Thank you, Professor.
Who is talking? Shaky?
Myself, Dilavesh.
Okay. So you would like to stop or just keep on going? Since you are being the spokesman too.
Sir, I think there's a break for 5 minutes.
Oh, you like a break. So what are you going to do with the break? You're going to drink a cup of coffee or what? Go ahead. Hey, look, I like when I teach a class in present, I like to play around, okay? So, Professor
But
Ali,
right now is the literature is easy now. You are teaching that we can understand it all.
can you understand what I'm talking? Is that what you said?
So you have teach the norm spaces and for the vector spaces, we got
Uh-huh.
that points, all points. So that's why some of them have not questioned you. Some of us have not questioned you.
Okay, so you said that nobody have a question. Is that what you said?
Yes, sir.
Yes,
Okay.
sir.
Oh, feel free to ask questions. Do you guys, this class goes until what? Until what, 9:30, 9?
Yeah, Prof. 9:30.
9:30. Okay, you want a 5-minute break? That's what someone said. They would like to be a break, right?
Yes, sir.
Yes, so that's okay. So I'll give you a 5-minute break. So you'll be back in 5 minutes, okay? You know, the reason I am talking about this stuff over here because you don't see many of these people when they talk for, you know, in general, the geometry of this, okay? Okay, so while people has a break, those who doesn't want to break and want you want to ask any question, you want to make some comments, please let's do so while you wait for 5 minutes or 10 minutes, okay? We have over here in Colorado is 9:28, over there is 8:28. So let's get started 20 minutes to 9, okay? So does anybody have any question? Does anybody have any suggestion? Does anybody have any comments? No comment? Man,
I
go ahead.
have a comment.
Okay.
I always have comments, some comments.
That's pretty good. That's the way. Mathematics is not matter of opinion. So, go ahead. Do your comment, Nozara.
Yeah, Prof. Prof, as we have seen a lot, I am commenting about general, as I have seen the papers from Professor Eddy, biological modeling, numerical.
Well,
There are many techniques of numerical analysis which are used in that paper. So we also combine functional analysis things. We combine many of the norms, Mayer theory, and then we go to find our basic biological model which we are going to find, or we want to model some problem. So am I right about it that we take all these criterias, all these things together?
yeah,
Some
that well, if you understood what you're saying, you have been using some of these norms in the stuff that are you doing. You can use any norm whatsoever. Okay, I particular with my experience, I use a norm that's convenient. If I have time, I'll give an example over here. That, for example, the Cauchy-Schwarz inequality that I'm going to mention when we come back, it can be a complicated inequality. However, if you use different norm, this inequality is basically not, is a half of a line. So one thing that people using the norm in Rn is, the whole idea is because all the norm in Rn, okay, basically the same because they are equivalent. So you are entitled to use whatever needed. Now, the only problem that you have when you start geometry, because the graph, I am going to do the graph in 2 dimension for you guys. The function, the norma 2 is differentiable, while the norma things is not differentiable in here, see? It's not differentiable. So this over here differentiable all over, and also this norm over here is differentiable when you study convexity. However, in the most thing that you do everyday life in analysis, you can use MLAW. Someone make a comment over here. Usman Tariq. Here you are use all this method by use a general and a simple example. Would you please give us a little bit complicated example or question and then use of this method to show how are to be used? Yeah, the other method that should be my next example is the LP norm, the LP space, and this is more complicated. Okay. Also, you have the D'Souza space. There is a space of function that I introduced a few years ago. The norm over there is a little bit more complicated. Okay, if you use complex functions, the hard spaces, that's going to be a little bit more complicated. My idea on this, you have all this as example on my books that I sent to you, because I don't have time to go in detail in all those examples. And if anybody see some example that you don't understand and would like to talk to me, okay, we can do it. We can set up some Google meeting and we can discuss and I can show you, okay. Yes, there is some more complicated stuff over there, and I am going to mention one over here when we come back, okay. Okay, that's Usman Tariq. Okay, I will give some example that you going to enjoy it. Okay, any more comments? Any more questions? Everybody's so quiet. Are you in class, having presential class or all the classes being virtual?
Prof, say again. What are you saying?
Sir, we have both classes due to COVID. Now we have a virtual classes.
Virtual class. Okay. Okay, but I have been lecture, in Brazil in virtual. Or that's the good thing because I was supposed to go to Senegal, and the virtual is making me not to travel that far because I travel a lot. I have been lecture in over 60 countries or even more than this country. And when you go to Africa, it's 2 days. I was invited for the wedding of Professor Ali Imisha. Going back and forth, that's 4 days from Colorado to Lahore, Pakistan. Okay. So the virtual class, it give us more opportunity to connect. So if anybody, you have my email over there, if you want to talk to me, even though I am a very busy person, but I try to make it available myself to all the students and try to answer all the questions that I possibly can. Okay? But I would like to see people make some more comments, some more questions. If you do not understand, if you have a question, to me, any question. There is no easy question. There is no complicated question. Please feel free to ask this question. I am going to answer the question of Usman Tariq. Did I get that all right? Usman Tariq. A more complicated example. If you want a complicated, I can. Wonderful class I never had. What was that? Yeah, thank you so much, Misha. Oh, I don't know. I wish I could. Muritaza Begi. So, kindly also explain graph the concept of equivalence relation, which we start early for normal space. Well, equivalent relation, equivalent norm is two different stuff. Okay, the equivalent norm. Yes, I can explain to this. I have to give the definition of equivalent norms. Okay, I will do that, Osman. Anand, right? Anand? Okay. I will do that. So I have two questions to answer. One is Miss Osman and the other one is Aina. Okay? So are they over there, right? I can answer right now. So, trying to answer the question of Usman, everything depends on the norm, right? Let's get the norm. Take x, let me put L2 on 0, 1. What this? This is the set of function from 0, 1 to R, such that the integral 0, 1 ft square dt 1/2 is finite. That they call the Lebesgue L2 space. Okay? Also, we have x is equal to LP space, which is the same except you have p in there, integral from 0, 1 ft p dt 1/p is finite, p bigger or equal to 1. Okay? Now, this is a norm, mainly when you consider that being a continuous function. At least I am going to skip some. Okay? So, this over here, to prove that this is over here is a norm, okay, you start getting into the problems over here. If F and G is an LP, it implies F plus G also is an LP. You get some little trouble over there, okay? 2, F plus G P is less than FP plus GP. That is more complicated though, okay? So you have really something complicated. In order to prove this over here, you have to use this. If A and B are positive, A, B, will be less or equal A to the P over P plus B to the P to the Q, where 1 over P plus 1 over Q is equal to 1. And this for A, B numbers. So you have to use this in order to prove this over here. So this example over here is more complicated, okay, to prove, okay? It's taking me a while to prove this over here. So if you said that, you know, something more complicated, this is one. Then you have some more examples. In my book, the notes over there have a lot of examples. Okay? Did I answer your question, Osman? He's there?
Yes, sir. Yes, sir. Yes.
Okay. So now let me answer the question that Anna. Okay? Let me go to the other side and say, you have a norm Rn. You have two norms, norma 1 and norma 2 in Rn. That's our norms. Okay? Now we say that norma 1 is equivalent to norm 2 if and only if norm 1 is less than a constant, norm 2 less than a constant, norm 2. And that is the equivalence. What's happening is all the norms in Rn are equivalent. This is the, let me put some colors in here. Fact. All the norms in Rn are equivalent. Okay? Now, I can prove easily for the norma 1, norma 2, and you know, we had shown that X norma 1 was less twice than the norm X and 2. See? We also show that the norm infinity is less than norma 2. You see? Now, let me prove this other inequality in here, okay? Since it's easy. Okay? Now, look over here. Norma 2 is the square root of x squared plus y squared. This is less than the maximum between this and this, right? This is less than the maximum. Square, right? and this is less than the maximum of x and y squared, right? So this over here, it would be twice what this normal is. That's the norm infinity, right? And this is the square root of x infinity. So this over here is square root of twice norm infinity. You see it? On this case, this is square root 2. On this case, over here is 1. Okay? Did I answer your question or no?
Yes, sir.
So, in analysis, we have a function, it's a metric function. Then why you need the normal function? I am going to explain to you what difference from metric function and a norm. It's two different animals. Can you find the distance with help of metric? Then why we need norm? Oh yeah. Metric is just a little piece of the puzzle. Okay, I am going to explain next. Okay, can you restart? Let me go and drink some water because I like to talk too much, and I'll be back in 1 minute, okay? Okay, guys, I'm back. Okay, now I answered the question of Anna. I answered the question of Usman. Now I am going to answer the question of Sadia. Is that Sadia or Sadia? Hello? Sadia. Okay. Okay, let's keep moving. Okay. We saw x plus 1 normed space. Okay. Now I'm going to write this definition. Let n be a set. Here's a set. a metric in M is a function D from M cross M into R plus, so that one, distance of X and Y, we call D distance, that's called metric, is 0 if and if X is equal to Y. 2, if you have dx and z that's less than dx and y plus dy and z. Third, the x and y is dy.
Equals dy.
The what? Okay? You have this definition on the page 5. Okay? And then if you have this called a metric space. Okay? Now let's comment about this. Okay? Okay. Okay, so I think that you cannot get my point. I said they kindly give example of normal space and solve by using 3 or 4 type of method that can use to find a norm. You gave us example, but don't solve it by 3. I don't understand your questions, man. You said, I think that you cannot get my point. I said that kindly give me an example of normal space and solve by using all the 3 or 4 type of method. What do you mean 3 or 4 types of method? What that means? We can use to find a norm. I don't understand your question. You gave us example, but you don't solve it by all the 3 or 4 methods. I don't understand. Can you talk and tell me exactly what you mean by that? Hello? Are you there?
Yes, sir.
Go ahead. What do you mean by 3 or 4 methods?
Sir, you tell us that norm 2, norm 1, norm infinity. These are 3 types to solve any norm.
No, what I'm saying that whatever problem you have, you can use any of those norms. So if you really want an example, I can do the Cauchy-Schwarz inequality. Okay?
Okay.
Cauchy-Schwarz inequality. Cauchy-Schwarz inequality is this. Cauchy-Schwarz inequality. The traditional one. Pick x is equal to x1, xn, y, y1, y2, yn. The inner product of x and y is x1, y1 plus xn, yn. So the Cauchy-Schwarz inequality says the following. If you take norm of this is a number, this is a number, this is less than this, less than this, okay? If you look on my paper that I mentioned that I published in Brazil, we gave different proof of this. But this proof over here is complicated, a little bit complicated. But instead use this, look what I'm going to use. I'm going to give a proof over here, okay? X and Y is summation of xi, yi, I from 1 to n. I'm going to take absolute value over here. I'm going to take absolute value in here. Now, this over here is absolute value of xi, absolute value of yi, I from 1 to n. Now, look at this over here. I am going to take the sup of this. So this is less summation I from 1 to n xi, the sup. I put maximum, right? Since it's finite. Maximum of y1, yn. See it? Now this is a number now. It's not on there. This now is a number. Okay, and this over here is y infinity, right? So what you have this slash or equal, this is normal y infinity. What's left over is x1 plus xn, I from 1 to n. What this over here is? This is norm x1. So what I have over here is this. Let me put some black. See? This is x and y is less than normal y infinity, normal x1. That's a Cauchy-Schwarz inequality. See it? This is too complicated to prove, and this over here. Whatever you use this, you can use this over here. And that's what I meant. You can use L. Okay? Because the normal is equivalent. Whatever you want to prove using this, you can use to prove this over here. That's what I meant. Did I answer your question? Usman, did I answer your question?
Sir, yes, sir. Actually, I was checked that you said that we can use norm 2, norm 1, norm infinity, or norm p
Any.
to solve. Yes, to solve to get answer.
Well,
Actually,
to prove this.
yeah, yes,
Now,
sir.
the point is, where are you going to use this?
Actually, I was checked that. I want to check that all these are give us same answer or different.
It's not the same answer, it's the inequality. Okay? So that means, where do you use this? You use this to prove the Riesz representation theorem. That's why you use this over here. Okay?
Yeah.
Now, if you want to prove this, that's a little bit more complicated. Now, his representation theorem, you can use this over here too. Okay? I can use any other inequality. I can use this over here. This is true. X and Y is less than the XP times YQ, where P and Q are bigger than 1, 1 over P plus 1 over Q is equal to 1. I can use the Riesz representation theorem for this. The point is, any norms, any two norms in Rn's are equivalent. So you are free to use whatever you want to.
Yeah, yes, sir, I got it.
Okay?
I clear my point.
Did I get the answer to you though?
Yes, sir. Yes, sir. I confused about equal sign and inequality.
You can
That's why
use any norm to prove
yeah,
inequality.
yes,
Use
sir. I
norm to
confused.
prove inequality.
Yes, sir. This is inequality. I thought like just like we solve equal answer.
Yeah,
Yeah,
you see how simple is this
that's
over
why I
here?
confused.
And the this over here is not that simple
Yes.
to prove. Okay? Okay, I'm
Okay.
glad that you got it. Okay, now let's back to medical space. Someone asked me my question over here. Now, let me ask one question. Can you see any difference between these two animals? This is a normal space. This is a medical space. Can you see any difference between them? Let's go, guys. Stop.
So scalar multiplication, the third property of norm spaces is not here. It could
That's
be
the,
solved, but
that's the big point. That's over here. Okay, there is no structure. Now, a normal space can be a metric space, but a metric space cannot be a normal space except this M over here is a vector space. Okay, and a plus some condition over here. This over here is a house where the only thing that you have inside the house is a bed to sleep. You have nothing. You have no wife, you have no TV, you have nothing. And this is a set. There is not, is a set. This over here is a set. You have a operation, and you have a norm over here. So this over here is richer. And this over here, the only thing that they have is a set and the norm. Any space, any set can be a metric space. Let me give an example right now. Okay? How many students you have over here? I believe that's 32. 32 students. Okay? This P over here is all the students attending my lecture. Right? Okay?
Okay, bro.
Okay, I am
yes,
going to find a norm on that space over there. On that set. It's a set. There is no structure over there. You can see it. So the norm that I'm going to define, P cross P, 0 to infinity. So I'm going to find the following. Pick a student over here, Nozara. Pick Misha. This is 0 if Nozara is equal to Misha. And is 1 if Nozara is different from Misha. And this is a metric. See it? So any set whatsoever can be made a metric space. Can any set be made a vector space? No, you can't. Unless you have two operations over there and satisfy all those 9 properties. So metric space is a set and a distance, nothing else. Does anybody have any comments? Now, a normal space can be a metric space. A normal space, okay? Let me get my break over here. Let x plus be a normed space. So define D from X cross X in 0, infinity by dx y is X minus, see it? This is a metric. So a normed space can be always be a metric space, but a metric space cannot be a normed space. Does everybody understand that?
Yes,
Yes,
Prof.
sir.
There is no structure on metric space. The way I used to say to my student, a normed space is a house with all the equipment, include wife. It's complete. Boom. A metric space is a house. The only thing that you have over there is a bed. You don't have anything else. Did you like the analogy? Come on, guys, talk some little bit. Okay? Now, metric space is very important because, for example, what Professor Ali is group over there study is metric preserving functions, okay? And that is a very interesting stuff. Which Miss Nozara and Miss Mission have done her thesis were the following. Let's see this example. Pick fx is equal to x1 plus x. Now, I am going to do this from 0 to infinity. To 0 to infinity. Well, over here should be 1, right? So, doesn't matter. Okay? Now, let d x and y be x minus y. Okay? Now, look, f composed with d of x, let's define d f composed with little d. What that means over here, okay? What this? I am d is, I am an r, cross r in 0 to infinity, x and y, send to dx and y, x minus y. Okay, now what this over here is? This is d, x and y, f composed with d of x and y. This is f of d, x and y, right? Now who is this guy in here? This guy is this. So this is d, this is f of x minus y. So this is positive, that's what the function is defined. What this over here is? This is x minus y, 1 plus x minus y, okay? And this is, see it? Now, point is this is a metric, and the capital D is a metric, and the f is this function over here, is they call metric preserving, because this is a metric D and this is a metric. Now the function over here have to satisfy some condition. In this case, this satisfies this condition. So that means if you have a metric D and you define another metric D, f composed with D, on certain condition F being increasing, satisfy some condition, this is a metric, and this is called metric preserving. And that's what stuff that Professor Ali have been studying. I'm just in touch because there's a metric space, and Nozara wrote a nice thesis in which I have the opportunity to read, and also master thesis. And Misha also had some of this. Okay. Does anybody have any question? Does anybody have any comments? You guys should be more spoken, outspoken. Should be outspoken.
Sir, we understand everything.
Oh, you do? That's nice. Excellent. So are you a PhD student over there in UMT?
Yes, sir.
Is that, who was talking? Was Zafar? What? Zafar, are you a PhD student over there? Oh, she left. Okay.
There are MS students plus PhD students
Oh.
in this.
Yeah, Nozara, you're going to be my spokesman. Next time that I will speak, you're going to be my spokesman.
Oh.
You are outgoing spokesman, so Okay, so they have norm. So the question is, what do you do with norm? Okay, I could mention a little bit topology over here, but I'm not going to mention. I am going to jump to other subjects. But remember, metric space and normal space is two different animals. They looks like the same, like fox and coyote. They looks like the same. Fox and dog, they looks like the same, but they are not, okay? A normal space can be a metric space automatically, okay? A metric space, a normal space can be, but not the other way around. A metric space can be a normal space if the space have the structure of normal space. No. A metric space, there is no operation in there. Now, people who use the theory of fixed point, they in general deal with metric space because it's easy to build up a metric space. To build up a normal space, you need to have more structure over there. Is anybody follow what I'm talking about? Come on, guys. Okay. Okay. So let's
Yes.
move to the other stuff. Okay.
Okay.
Now you have I have two more definitions over here for us to have more good time over here. Okay. Is this? Okay. I have x plus
So time is about to end.
normal space. I'm going to give a definition one. A sequence xn in X is said to be convergent to X if, let me use the easy notation, limit as n tending to infinity, xn minus x in X is 0. Or if for every positive x there is a n such that if n is bigger than n, it implies x minus x is less than epsilon. That's the definition. This is the epsilon delta definition. Okay, so that means a sequence is said convergent if this limit is 0. Let's see some example. Pick xn is equal to 1 over n. Pick my space x0, 1. This sequence over here, xn converges to 0 as n to infinity. Okay? Then you have 2. A sequence xn in x is said to be Cauchy sequence if limit xn and xn as n and m goes to infinity is 0. Get it? That's called Cauchy sequence. Let's see some of the difference between one. If the sequence converges, the sequence is Cauchy. But if the sequence is Cauchy, not necessarily is convergent. Okay? Now, let's try to understand over here. On this over here, you have to have a limiting point. This over here, you are measure the distances between point as n and m goes to infinity. Okay? So a convergent sequence is a Cauchy sequence. I can prove this very easily. Okay? But a Cauchy sequence not necessarily be a convergent sequence. Now, the Cauchy sequence deal with the distances for m and m very big between points in here. Okay? Now, what this says over here, you have a point in x in here. Okay? That's this x element. Okay? Now, what this happen is, if n is very big, all the points is close to x. That's what the limit says. All the points close to x. Okay? But this over here tell all the points xn and xm, if n is big, they are close to each other. But there is no leading point over there where they are. Now, this is very important to understand this, because now we're going to define what the meaning of Banach space. A normed space is a Banach space if every Cauchy sequence is convergent. And that's the major concept that most people in analysis to work. That is the Banach spaces. Okay? So what is a Banach space? A Banach space is a normed space where every Cauchy sequence is a convergent sequence. Okay? So now we are putting more stuff on this over here, right? So let me put the definition in here. Does anybody have any question? See over here. A normed space X is a Banach space if every Cauchy sequence is convergent. And that's the definition. So now my structure gets bigger in here, right? Because now you have a normed space, then you have a structure of Banach space. So this over here is being refined in that, okay? Now, what makes a Banach space is the norm. See, the norm is important to make a Banach space. I am going to give an example over here. If you switch the norm, the space is not any longer a Banach space. Let me give an example. Pick a continuous function on 0, 1 with the sup norm. Okay? What the sup norm is the supreme of fx, x on 0, 1. Now, pick the continuous function with the L1 norm. That means FL1 is the integral on 0, 1 ft dt. Okay? Now, look at this. This C1 is a Banach space. C1 with the L1 norm is not a Banach space. You see it? Now, let me try, we don't have much time in here, to give an example so you get familiar with this. Okay? Pick fx is equal to x squared in 0, 1. So the graph of this function is this. Okay? So what the sup norm of this? What the sup? This, right? 1. Okay? What the L1 norm of this is the integral 0, 1 x squared dx is 1/3. You see? This norm over here is smaller than this norm in here. See it? This is 1, I'm just giving an example, and this is 1/3. This is a complete, this is a Banach space, and this is not a Banach space. Okay? Let me show this is. The idea here to show this is not a Banach space is to give a sequence that is Cauchy but not convergent. Is everybody understand what I'm talking about? It's very important to do this because now we get into on the theory of Banach space, okay? And it's important you understand the concept. The point is, if you have a normed space, if that norm make it a Banach space, that's a very special norm. Okay, in Rn, all Rn with any norm is a Banach space because the norm are equivalents. But on this case over here is not. If this norm were equivalent to this will be a Banach space if and only if this is a Banach space. But the norms are not equivalent. There is no other inequality in here. See, this doesn't exist. Okay? Now, trying to understand this over here. If you pick a Cauchy sequence over here, this is a convergent sequence. That means there is a continuous function for which that Cauchy sequence converges. This over here, I am going to show you that there is a Cauchy sequence for which the limit is not in the continuous function. Okay? Since I have 6 minutes, I don't want you, that's too late over there, I know. I am going to show this over here to you, okay? Show that there is a Cauchy sequence for which is not convergent. Does anybody have any question? No, Zara, have any question? No, you have any question?
No, Prof.
No, sir.
Who was the other one who spoke? Osman, do you have any question? I'm going to do this geometrically.
No, bro.
I am going to define the following function.
No, sir. Sir, this is 9:25.
That's all right. I need 5 minutes. It's just to finish it 9:30, right?
Okay, all right, sir. Thank you.
Okay. Okay. I'm going to put any x if 0x is 1 over n. And I make 1 if 1 over n is less than x, less than 1. Let me graph this function over here, okay? I have 0, 1 in here. I have 1 over n in here. Now, this function is aligned to the origin. That's it. This point over here is 1. If x between over n and 1 is get 1. If between 0 and over n, you get this. Now, look over here. If there is injustice on the world, what's happening if n goes to infinity in here? Where this converges?
0.
They converge to 1. Okay? So this function
Okay.
converge to the function 0 at 0 and 1 if x different from 0. See it? And this function over here is not continuous function. Now, is this a Cauchy sequence on the L1 norm? I want you to take a look on this over here, okay? Now, I'm going to do geometry. I don't have much time over here, okay? Now, if you have another point, 1 over n. So you have fn minus fn. So I want to estimate integral fn minus fm1 is the integral 01 fx n minus fmx. We can do this geometrically. Now look over there. What this integral is? This integral is this area over here, see? Area of A, that's what this integral is. Now what's happening if n and m goes to infinity? This line and this line is going to collapse in here, so this over here tends to 0 as n and m goes to infinity. So that's an example of a Cauchy sequence in C01. Fn is a Cauchy sequence in C01 with this norm 1, but it's not convergent. Okay?
Yes, sir.
Okay, is anybody have any questions? Anybody have any? I know that's late. It's time to kids go to sleep, right? That's what you're going to do over there, right? Okay. Does anybody have any question? I did not have time to get to the next step, which is important. If Ali allow, I will not mind to give another talk in the talk about linear transformation. That's in his representation theorem. But in the meanwhile, this over here have everything in here example. If you have any problem, my email is right on the second page. My email is just on the second page over here. Have added to his email over here, right? That's my beautiful university. This is Ed's beautiful university, and that's the place that before I go to my resting place, I want to visit this place over here. Okay. But anyway, if Ali gives some time, I can continue sometime to finish this. This is overall picture. Okay, what we have dealt right now was Normed space, Banach space, and metric space. And the structure of norm, the structure of the metric, and also everything that we done in Normed space is a mirror of real numbers. Okay, real numbers are the complete metric space, is complete Normed space. Continuous function is a complete Normed space if you define. When you have two spaces, except in Rn, I stress this, you have two Normed space over here, not finite dimension, not Rn. Okay, if you put a norm on this over here and they put different norm, that's two different animals. Even though that you have the continuous function, with this norm, that's a Banach space, this is not. This is good and this is not. But the spaces are the same, but the norm are different. The topology, the way that you measure the function. Okay? Okay? I enjoy very much, even though that just a few people were able to talk, okay? And I enjoy very much. I will give to Professor Ali to give the final word over there.
Thank you so much, sir. Sir, we also enjoyed your.
Thank you so much, sir.
Thank you.
Sir, thanks a lot.
Yes, hello, Professor. Thank
Yeah,
you very
I
much.
listen. You can go.
Sir.
Go ahead. So right now, Professor Ali is the one who is in charge. I am just listening. You probably heard that what I said, right, Professor Ali, that we didn't get to the Normed spaces, but if you allow, I don't mind to give another talk on this, Normed spaces, because this is a overall picture that's going on. We are trying to go in details and things that you probably have seen, but I let you decide. Okay, guys.
Yes, Professor, we
Okay,
can
sir.
arrange another lecture. Hello?
Yes, sir.
So the people from Pakistan, they don't like to talk. They are very quiet over there, isn't it? Just